Speaker is Yanick Schraner. He will tell us about an evaluation of speech-to-text systems. As far as I heard, it was about 3 of them. Yeah. So about 3 different speech-to-text systems, and I'm very tense to hear the results.
Okay. Hello, everyone, and thank you for the introduction. I have to speed up now a little bit because we are in a delay. My talk is about the evaluation of different speech-to-text systems for Swiss German. In my group, together with Manfred, with Christian, and with Michel, we are working since the last 3 years on speech-to-text systems for Swiss German. And actually, we should call it speech translation systems because we have as an input Swiss German audios, and as an output we create standard German text, because Swiss German is basically a spoken language, and there is no real formal way on how to write Swiss German, and it's only used for informal texts like text messages. So we are going to compare 3 different commercial available speech-to-text systems for Swiss German and compare them to our own developed speech-to-text system. The data that we use for this evaluation is created together with our colleagues from the ZHAW and from the USI, and we collected data from 7 different dialect regions in Switzerland. We marked them here on the map of Switzerland, and basically we collected for all those 7 dialect regions, we collected 5 hours of audio. So in total we have a test corpora containing 35 hours of speech data. Here in this plot you see the age and gender distribution over the collected data. When we collected that data, we tried to have more or less even distribution between the gender and also between the age groups, so that we can tell if if systems are too biased towards male or female voices or biased towards a certain age group. Here we have a plot of the durations of the single utterances contained in our test corpora, and we can see that on the x-axis we denote the duration of those utterances, and on the y-axis we have a frequency count of those different durations, and we see that on average one utterance is about 5 seconds long, and the shortest utterance is 2 seconds long, and the longest about 11 seconds. The data is collected, maybe some of you know dialektsammlung.ch, that was an initiative, and Manuela Hürnemann is going to talk about that in the next talk. And in the data we collected here is very similar to how we collected the Dialektsammlung. We present the speakers with sentences from the domain of news and parliament data, and they see a standard German sentence. They have to translate it in their mind into their Swiss German dialect, and then they have to activate the microphone on their mobile device or on their notebook, and then voice the Swiss German translation of that standard German text and record it, of course. And in total we have 3,602 sentences for each dialect region, and for the sentences are the same for every dialect region. We do that because we want to make sure that the vocabulary is the same for each dialect system, so that not maybe the canton of Zürich has easier vocabulary than the canton of Wallis, and so that we have a fair comparison between those dialect regions. One example for those sentences is darauf zeigte A.M. ihn an, and here I have 2 records of these sentences, and I will play them shortly. I hope this works. Doesn't look like it, but that's not the problem. So what I wanted to show with those two audios is that in the first one, the speaker says, darauf hat der M ihn angezeigt. And in the second one, the speaker says, darauf hat A.M. ihn angezeigt. So the difference between those two speakers is that one pronounces the punctuation and the other one doesn't. So basically, both recordings are correct. They are correct way on how to say that sentence in Swiss German, but they formulate it differently. And that's one thing that we have to take a look at when evaluating the speech-to-text system, how they are handling those differences, if one thing works better than the other or not. Okay, the metrics that we are using when evaluating the speech-to-text systems are the Plüss score. That's a metric that originates from machine translation systems and is also standard in speech translation systems. It basically is a score between 0 and 1, and it measures how good the translation maps to or matches a set of reference translations. The problem in our evaluation is that we have only one reference translation and not a set of reference translations. So that's suboptimal for when you use Plüss score. And the second metric that we are using is the word error rate. That's basically a derivative of the Levenstein distance, but not on a character level, but on a word level. And it measures how many word substitutions you have to do to end up with the same sentence. Okay, now let's talk about the results. So we have 4 different systems. We discussed with our partners that we keep them anonymous and we don't say which system is from which company, so we just call them system A, B, and C. And on the bottom of the table, we have our own system. We denote it as FHNW. And we report 2 scores, the word error rate and the Plüss score. It is better to have a low word error rate and a high Plüss score. So best word error rate will be 0% and best Plüss score will be 1. And we see that system A and B have a similar Plüss score, but a different word error rate. So you can see that those 2 scores don't really correlate. You have to keep that in mind. And we also see that our system is by far the best one. We have almost half of the word error rate compared to the other systems. But we also have to be fair that probably the text data, probably the training data and the test data are very similar because we use the part of the Schweizer Dialektsammlung for our training. And as I already said, the test data is collected in a similar way, so they are somewhat similar. Of course, they're not containing the same data. And also our language model that we use is trained on data in the context of news and parliament speeches. And here I told you that the sentence that the participants have to record were also in the same domain. So probably this also has an influence on the scores that we're seeing here. In this table here, we now report the metrics on different dialect regions, and this allows us to see if one system fails on one dialect specifically, or if one dialect is specifically difficult for each systems, or if one dialect is easier than others. And what we see here is, what's this? No. Okay, what we see here is that Wallis is that one dialect that works the worst. It has the lowest Plüss score and the highest word error rate. And for those of you who are familiar with Swiss German dialect, I think they can relate to, because Walliserdeutsch is far away from the other dialects and it's not that easy to understand. And the other thing that system B is especially bad on Wallis dialect. And the other thing that we can see is that Zurich German and Innerschweiz, they are both pretty easy for the systems. Here we see the highest Plüss scores on all systems. Probably one possible reason is that they are closer to Standard German than the other dialects, and I think all of the systems use also Standard German speech-to-text data in their training, and probably from there the transfer is easier from Standard German to Zurich Deutsch or to Innerschweiz Deutsch. And the other dialects, Basel, Bern, Ostschweiz, they are almost on the average. So nothing special to see there. We also performed another evaluation where we searched for sentences containing named entities. So we used Spacy to detect named entities. For those who don't know what named entities are, for example, names, or it could also be company names, it could be places like Basel or Zürich. It could also be numbers, depending on the named entity recognition system. So we search for sentences containing named entities, and then we evaluated the systems only on those sentences and calculated the Plüss score. And what we see is that all systems, they really suffer especially bad on sentences with named entities. For example, our system loses about 11 blue points on sentences with named entities compared to the whole test corpora. And here as well, system B is the one who has the most trouble with named entities. Now I want to go through some example sentences and see what we can see here. This sentence should be familiar to you because that's the one I talked about in the beginning. And we can clearly see that, for example, system C now writes Punkt, A Punkt, M Punkt, and doesn't write it as a dot. And other systems like system A completely fails with that sentence, and our own system has as well their difficulties. So this sentence is also one that got detected as a named entity, and we see that with abbreviations almost all systems have their problems. This sentence is also interesting. I didn't know that it was part in our test corpora because basically it is an English sentence and it shouldn't be here because we are looking for Standard German to Swiss German pairs. But it's also a common phrase to say in Switzerland, last but not least. And what we can see here is that system A and system C, they have no problems at all with English sentences, so they work very well on that, while our system fails completely once it got it right. I would say that one possible explanation for that is our language model is only trained on German text, and I assume that last but not least is not part of our language model, and that the language model probably forces or falsely corrects some things, and also system B fails completely. Here we have another a little bit longer sentence, and it is interesting because of two reasons. First reason is here we have FDP, which is a named entity again, and we have Dereglementierung, which is quite an uncommon word. Usually, or more usual, you read Reglementierung, which means regulations, and Dereglementierung means reversal of the regulations. We see immediately that all systems correctly transcribe FDP, and I think it could be because FDP is a rather common named entity, and it is also for sure part in standard German corpus, as this political party also exists in Germany under the same name. Therefore, I assume that it is a common named entity that is also part of the training data. So we see if named entities are part of the training data, then probably it will also work good. And our system was the only one that was able to transcribe Dereglementierung. In System C, we see a funny effect. We have here eine Dereglementierung. So it separates us in two words and makes de to die. Now I want to go briefly over our own model so that you can see what exactly we trained and you get a little bit of insight into that. But I have to hurry, I'm a little bit in a delay. So for our model, we used the XLSR 1 billion model. This is a model published by Meta AI. Maybe you know it under Facebook AI. It's the same thing now. And XLSR 1 billion is a rather big model. It is trained on 436 hours of speech recordings, containing 128 different languages. So they use a lot of data, and they applied Wave2Vec 2.0 pre-training. That's also a paper they published, I think 2 years ago. And it is a training strategy to use unlabeled data to get good embeddings for your speech data. And then for fine-tuning, we used the STS200 dataset that Manuela is going to talk about. Then the Swiss Parliament corpus that is also a corpora that we published, I think 2 years ago, and Swiss style corpora published by ETH. And here are some hyperparameters. I'm not going over them because not too interesting. So in total, we had about 450 hours of Swiss German speech data for the fine-tuning. And we also used a language model. That's a KNLM 4-gram language model trained on 67 million sentences. They are all in the domain of news and parliament data. So I think I'm going to skip this slide and not going into detail how Wave2Vec and XLSR works. But I wanted to draw your attention to our demo application. Our team recently published our best model under that URL, and you can go to that website. Let me see if this works. You can go to that website, and here you see a card. You can click on it. Hallo, ich trinke gern Wasser. Then you can click again. It will be recorded. Okay, that was a super bad example. Let me do it again. Ich trinke gern Wasser. Oh, okay. So I will just talk about it. Yeah, you can interact with that web page. You can click on the microphone, then you can record your own Swiss German sentence. Click again, and then you see a transcript, and you're very welcome to test that service. But if you test it, please also rate the transcripts, because that would be very useful for us for future work, to see what worked, what didn't really work, and maybe also to improve our metric evaluation. Now I have just a little bit of time to answer your questions.
Thank you. Thanks again for the talk. I was just wondering, I think you trained your data with, so you use data in news and was it parliamentary data or something like that? Have you thought about changing or using any other domains?
Regarding the language model or regarding the language model?
Yeah, exactly.
Yes, initially we had also sentences from Wikipedia and so on, but the problem there is that some of the test data also originates from or some not on that test corpus, but other corpus that we have, they originate from data from Wikipedia, and we wanted to be safe that we have no data leakage between the language model and the audio data. But yes, we also experimented with other domains for language model training.
So did you choose the language model KNLM? Was it a choice on the code bases you're using, or was it also already pre-given? Because I know it's 128 languages, and the languages in between, they can, let's say, it's not transfer learning, but we are humans, how we're uttering. The acoustic model is definitely benefiting from the 436,000 hours in the acoustic space. But the problem is when you've shown your last but not least, you just didn't cover it because apparently this KNLM is then just for German language, I guess.
Yeah.
Whereas, so the question is, doesn't this XLSR offer a language model off the shelf, which is then covering all the languages? And also the language switch we have seen.
Okay, XLSR is only on audio data, and it's unlabeled data, so there we don't have really text. Of course, some of the 436 hours, they also contain text, and it would be possible to use that text to train your language model. But as we are only interested in German text, we only focused on German data. But I would say you're right that we could augment the language model with more named entities and also with English sayings that are common in German. That's for sure going to help.